On October 29th at 11:47 Universal Time, 3I Atlas will reach its closest point to the Sun. For a normal comet, this is a moment of violent transformation. For 3I Atlas, it's something else. Because for the entire critical period, it will be completely hidden from every telescope on Earth. And that timing isn't a coincidence. That timing is a window of opportunity. This isn't about conspiracy, it's about data, and the questions that data refuses to answer. On October 21st, 3I Atlas entered solar conjunction. That means it passed directly behind the Sun from Earth's perspective. For 8 days, every ground-based telescope on the planet lost line of sight. The timing is notable. Solar conjunction occurred 8 days before perihelion. Perihelion is the closest approach to the Sun. It happens October 29th at 11:47 Universal Time. When 3I emerges from behind the Sun in early November, it will have been heated to temperatures it has not experienced in millions, possibly billions, of years. The question is not whether it will change. The question is how much, and whether we'll be allowed to see it. You know what happens when comets approach the Sun? Sublimation. Ice turns directly to gas. Pressure builds beneath the surface. Vents open. Jets form. The coma expands. Tails develop. One made of ionized gas pushed by the solar wind, another made of dust particles drifting along the orbital path. This is normal. This is expected. Except 3I Atlas is not behaving normally. The object began outgassing at 6.5 astronomical units from the Sun. That's 970 million kilometers. At that distance, solar heating is negligible. Water ice doesn't sublimate until you're inside 3 astronomical units. Carbon dioxide can activate earlier, around 5 astronomical units, but not at 6.5. Yet the Zwicky Transient Facility detected a coma in May 2025, when 3I was still beyond Jupiter's orbit. The coma was faint but measurable. Dust production rate estimated at 5 kilograms per second. That's not a lot, but it's something. And it was happening when nothing should have been happening. The brightening curve is wrong. Most comets follow a power law. Brightness increases with the inverse square of distance to the Sun. 3I Atlas follows an exponent of negative 3.8. That's steeper than it should be. It means the object is becoming more active more quickly than thermal models predict. Independent observations from the Nordic Optical Telescope, Palomar, Keck, and the Very Large Telescope all confirm the same trend. The activity is accelerating in a way that suggests either an unusually volatile composition or an internal energy source that has nothing to do with solar heating. By mid-July, 3I was at 4.5 astronomical units. Hubble captured detailed images. Coma diameter approximately 10,000 kilometers. Distinct asymmetry. The densest concentration of material pointed toward the Sun, not away from it. That's unusual. Comets generally show maximum outgassing on the Sun-facing hemisphere, but the ejecta quickly gets swept into the anti-solar direction by radiation pressure. 3I's coma remained stubbornly sunward for weeks. Only in late August did a conventional tail begin to form. The delay suggests that the dominant particles in the coma are large, around 0.1 millimeters in radius, and moving slowly, around 5 meters per second. Small grains, the kind that normally create bright visible tails, are conspicuously absent. Either they're not being produced or something is preventing them from escaping. Then there's the chemistry. This is where things stop making sense. James Webb Space Telescope observed 3I Atlas on August 6, 2025, at a heliocentric distance of 3.32 astronomical units. Near-spec instrument, wavelength coverage 0.6 to 5.3 microns, integration time sufficient to resolve individual molecular bands. The spectrum shows carbon dioxide. A lot of carbon dioxide. The coma is dominated by it. The mixing ratio of carbon dioxide to water is 7.6 to 1. For context, the average comet has a ratio of about 0.05 to 1. 3I Atlas has 150 times more carbon dioxide than expected. It is the highest CO2 to water ratio ever measured in any comet, solar system, or otherwise. The spectrum also shows water vapor, carbon monoxide, carbonyl sulfide, water ice, and dust, all expected, all normal. But the overwhelming dominance of carbon dioxide is not. There are only 2 ways to explain it. Either the nucleus of 3 I Atlas formed in an environment with extraordinarily high carbon dioxide abundance, perhaps near the CO2 ice line in a protoplanetary disk around a star very different from the Sun, or the surface composition has been altered by prolonged exposure to high-energy radiation during its journey through interstellar space. Both scenarios imply an origin far outside anything we consider typical. The carbon isotope ratio provides another clue. Carbon-12 to carbon-13 is measured at 83 plus or minus 19. That's within error of Earth's ratio, which is 89. It suggests the carbon in 3 I Atlas condensed in a stellar environment with similar nucleosynthesis history to our own Sun. That's good, that's normal. Except if the comet is billions of years old, if it formed in the thick disk of the galaxy, as orbital dynamics suggest, then it predates the Sun by 3 billion years. The isotopic similarity implies that the galaxy's carbon budget hasn't changed much over that time. It implies uniformity. Or it implies something else, something we're not considering. The Very Large Telescope detected atomic nickel in the coma. Not nickel compounds, not nickel ions, atomic nickel vapor. The emission lines were strong, 22 separate transitions identified in the ultraviolet spectrum. Production rate at 2.85 astronomical units measured at 4.7 times 10 to the 22nd atoms per second. That's roughly 5 grams per second. The nickel emission began at 3.9 AU and strengthened as the comet approached the Sun. Spatial distribution shows maximum concentration within 2,000 kilometers of the nucleus. That's consistent with a parent molecule releasing nickel atoms through rapid photodissociation. Here's the problem. No iron was detected. Not a single iron emission line. In every natural object we've studied, every comet, every asteroid, every meteorite, nickel and iron occur together. They form in the same supernova events. They condense into the same mineral phases. Their abundance ratio in the solar system is roughly 20:1 iron to nickel, but in 3 I Atlas, iron is absent, nickel is present. The decoupling is unprecedented. There are hypotheses. One possibility is that nickel is being released from a low-temperature carrier, something like nickel-carbonyl, nickel bound to carbon monoxide in a volatile complex that sublimates at very low temperatures and dissociates instantly in sunlight. Nickel-carbonyl is an industrial compound. It's used in refining pure nickel from ore. It forms naturally only under very specific conditions. If 3 I Atlas is producing it, that suggests a coma rich in carbon monoxide at low temperatures, which matches the Webb telescope data. But it doesn't explain why iron isn't following the same pathway. Iron pentacarbonyl exists. It's chemically similar. It should be there. It isn't. Another hypothesis involves organic molecules. If the comet's surface contains complex carbon compounds, polycyclic aromatic hydrocarbons, fullerenes, organic polymers, and if nickel atoms are embedded in those structures at the molecular level, then ultraviolet photolysis could liberate the nickel without releasing iron. That would require a very specific formation environment. It would require chemistry that doesn't happen in our solar system. Cyanide was detected. CN emission appeared on August the 14th at 3.07 astronomical units. Production rate measured at 2.1 times 10 to the 23rd molecules per second. The emission strengthened rapidly over the following week. By August 21st, production had increased by a factor of 3. The heliocentric distance dependence follows a power law with exponent -9.4. That's extremely steep. It suggests a parent molecule, probably hydrogen cyanide, sublimating from a localized reservoir that is only just beginning to activate. Cyanide is common in comets, but its sudden appearance, combined with the nickel emissions, creates a chemical portrait that doesn't match anything in the existing database. Water was detected, but barely. Hydroxyl radical emissions, the ultraviolet signature of water dissociation, were measured by the Neil Gehrels Swift Observatory. Production rate at 2.9 AU was 40 kilograms per second. That sounds like a lot until you compare it to the carbon dioxide production rate, which at the same distance was 300 kilograms per second. The water is there, it's just overwhelmed. And it began sublimating far earlier than it should have. Water ice doesn't activate until inside 3AU. 3I Atlas was releasing water at distances where water should have been frozen solid. The dust is strange too. Particle size distribution skews heavily toward large grains, effective radius around 0.1 millimeters. In normal comets, the dust population is dominated by micron-scale particles, tiny grains that scatter sunlight efficiently and create the bright diffuse coma. 3I Atlas ejects mostly larger particles that fall quickly and don't scatter much light. The Hubble images show a relatively compact coma despite significant outgassing rates. The missing small grains could indicate strong cohesion, particles sticking together due to electrostatic forces or organic binders. Or it could indicate that small grains are being destroyed or reabsorbed shortly after ejection. Either way, the size distribution is anomalous. There's also the anti-tail. Most comets have tails that point away from the Sun. 3I Atlas briefly displayed a tail pointing toward the Sun. The feature appeared in mid-August and persisted for about a week. It wasn't an optical illusion. It was real material moving in the sunward direction. Anti-tails occur when large dust grains lag behind the comet's motion and create a trailing structure that, from certain viewing angles, appears to point forward. But 3I's anti-tail was unusually prominent and lasted longer than geometric models predict. Some observers noted that its orientation changed slightly over several days, suggesting either rotation of the nucleus or time-variable outgassing that altered the particle trajectories. The rotation period is 16.16 hours. Light curve amplitude is 0.3 magnitudes. That's a relatively modest variation, suggesting either a near-spherical nucleus or a viewing geometry that minimizes the projected area changes. The rotation is stable, no tumbling, no precession. For an object that has been traveling through interstellar space for millions of years, possibly encountering debris, radiation pressure imbalances, and gravitational perturbations from passing stars, that level of rotational stability is noteworthy. It's possible. But it's precise. The color is red. Spectral slope in the visible range is 18 to 22% per thousand angstroms. That's similar to trans-Neptunian objects and some outer solar system comets. It indicates a surface rich in organic compounds, tholins, complex hydrocarbons, maybe even amino acid precursors. The red color is consistent with long-term exposure to cosmic rays. Radiation darkening and reddening are well understood processes. Over millions of years, ice and simple molecules get broken apart and rearranged into more complex, less volatile, redder substances. If 3I Atlas has been traveling through the galaxy for as long as its trajectory suggests, its surface should be red. And it is. So far, that fits. But then there are the gaps, the missing data, the things that should have been observed but weren't. No methane. Methane is common in comets. It should be there. Webb's spectral range covers the methane bands. Sensitivity is more than adequate. But methane is absent. Either the nucleus doesn't contain it, or it's not sublimating, or something is consuming it faster than it can accumulate in the coma. No ammonia. Same problem. Ammonia is a standard cometary volatile. It wasn't detected. No formaldehyde. No acetylene. No ethane. The coma is chemically simple. Water, carbon dioxide, carbon monoxide, cyanide, nickel. That's almost the entire inventory. For an object that's supposed to be a pristine sample of another star's planetary system, the diversity is surprisingly low. Then there are the institutional silences. On October 21st, the International Asteroid Warning Network, IAWN, announced a coordinated observing campaign. Duration, November 27th to January 27th. Objective: refine the astrometric position of 3I Atlas and test international response protocols for fast-moving objects. The announcement described it as a training exercise, first of its kind, entirely routine. The timing is interesting. The object will be observable again in early November after perihelion. By late November, it will be farther from the Sun, cooling down, outgassing less, becoming harder to study. The campaign begins exactly when the object transitions from active to quiescent. You could interpret that as efficiency, study it while it's still detectable. Or you could interpret it as timing designed to avoid the most dynamic phase. NASA's Planetary Defense Coordination Office issued an update on October 23rd. Short statement. 3. I-Atlas poses no threat to Earth. Closest approach to Earth occurs December 19th at 1.8 AU. No planetary defense measures are required. The object will exit the inner solar system by March 2026 and will not return. Standard language. Standard reassurances. The statement included one additional line. All observations are being coordinated through established international frameworks to ensure data sharing and transparency. That line wasn't in previous updates. Its inclusion suggests someone asked a question. The answer is the statement. The statement says everything is fine. On October 24th, rumors appeared on social channels. Anonymous posts claiming leaked documents, descriptions of classified briefings, references to Section 7 protocols, black budget allocations, Space Force coordination with NASA. Most of it is noise, most of it is unfounded, but noise often contains signal. When you sort through the claims, a pattern emerges. Multiple sources, unconnected, describing the same thing. Observations during solar conjunction. Data acquired by assets that aren't publicly acknowledged. Spectral anomalies. Thermal signatures inconsistent with passive solar heating. References to something called event threshold alpha. You can't verify it. By definition, you can't verify it. But you can look at what's public and ask whether it fits. The ExoMars data from October 3rd has not been released. The NOMAD spectrometer observed 3 I-Atlas for 7 consecutive days. High-resolution infrared spectroscopy. Sensitivity sufficient to detect trace gases at parts per billion. The data exists. It was acquired. It was transmitted to Earth. Processing takes time, but not this much time. Mars Express attempted similar observations. The results were described as inconclusive. That word, inconclusive, appears frequently. It's used when the data exists but doesn't support a clear interpretation, or when the interpretation exists but isn't ready to be shared. Europa Clipper launched in October 2024. It's en route to Jupiter. Current position, outbound, approximately halfway between Earth and Jupiter. Trajectory analysis published in mid-October by researchers at the Applied Physics Laboratory suggests the spacecraft will pass through a region where 3I's ion tail is predicted to intersect its flight path. The crossing window is October 30th to November 6th. The spacecraft carries a mass spectrometer. It carries a magnetometer. Both instruments are designed to detect solar wind disturbances and ionized particles. If 3I's tail is dense enough, Clipper will fly through it. The encounter wasn't planned. It's a coincidence of geometry. But it's an opportunity. Whether the data will be released is another question. Hera launched in October 2024. It's en route to the Didymos binary asteroid system. Current position, also between Earth and Mars. Trajectory models suggest Hera will pass through the predicted ion tail of 3I Atlas during the same time window, October 25th to November 1st. The overlap with Clipper is not exact, but it's close. 2 spacecraft, different missions, different destinations, both crossing the same volume of space during the week 3I passes perihelion. The probability of that happening by chance is low. Not impossible, but low. It suggests someone calculated the trajectories in advance. It suggests someone wanted in situ measurements. No mission adjustments have been announced. The spacecraft are following their nominal flight plans. But flight plans have margin. Instrument schedules can be adjusted. Data collection windows can be prioritized. If you wanted to observe 3I's tail without calling attention to it, you would use assets that are already in the right place. You would collect the data as part of routine operations. You would process it quietly. You would release it later, when the context has faded and the public's attention has moved on. On October 27th, Harvard astrophysicist Avi Loeb issued a public statement. He urged people to pay attention to October 29th. He suggested taking time off work. He described 3I Atlas as potentially the most significant astronomical event in modern history. Loeb has a history of controversial statements. He proposed that Oumuamua might be an alien probe. He suggested that interstellar objects could carry microbial life. He's not always right, but he's not always wrong. His statement was brief. It referenced the mass of 3I Atlas Pallas, 33 billion tons, and questioned why an object so large would be delivered to the inner solar system when previous interstellar visitors were orders of magnitude smaller. He used the phrase delivered, not arrived. Delivered. The choice of words is deliberate. It implies agency. It implies intent. Loeb also mentioned the nickel emissions. He noted the absence of iron. He cited unpublished analyses suggesting the nickel-to-iron ratio is inconsistent with natural nucleosynthesis. He stopped short of claiming the object is artificial, but he didn't dismiss the possibility. He described it as an open question. He called for more data, more transparency. He suggested that if the object exhibits further anomalies during perihelion, if the outgassing pattern changes in ways that can't be explained by solar heating, then alternative hypotheses should be considered. He did not specify what those hypotheses might be. 2 weeks before perihelion, the object was imaged by the Gemini South Telescope in Chile. Integration time, 90 seconds. The image shows a bright central condensation surrounded by a diffuse coma extending roughly 50,000 kilometers. A faint tail stretches antisolar for approximately 100,000 kilometers. The tail is asymmetric. Brightness variations along its length suggest episodic ejection events, bursts of material released at different times, creating density waves that propagate outward. The nucleus is not resolved. At the distance of observation, even Gemini's resolution isn't sufficient to separate the nucleus from the inner coma. But the image shows something else, a faint linear feature extending from the nucleus in a direction 30 degrees off the Sun-Comet line, length approximately 10,000 kilometers, duration uncertain. It appears in one image and is absent in images taken 3 days earlier. The feature could be a jet, it could be a dust streamer, or it could be something else. The image was shared publicly. The feature was not mentioned in the caption. On October 25th, an encrypted transmission was intercepted by amateur radio operators monitoring deep space network frequencies. The transmission originated from the vicinity of 3I Atlas. The signal was brief. Duration approximately 40 seconds, modulation pattern consistent with standard spacecraft telemetry, but the encoding was unrecognized. Attempts to decode it failed. The transmission could have been noise. Solar radio bursts occur frequently. Coronal mass ejections produce broadband emissions that can mimic structured signals, but the timing is notable. The signal appeared while 3I was behind the Sun, inaccessible to ground-based observers, in the window when classified assets could observe without public oversight. The signal has not been explained. NASA has not commented. 3I Atlas will reach perihelion on October 29th at 11:47 Universal Time. Closest approach to the Sun is 1.36 astronomical units. That places it between the orbits of Earth and Mars, closer to Earth's orbit. At perihelion, the comet will be moving at 68 kilometers per second relative to the Sun. That's its maximum velocity. After perihelion, it will begin to slow down, not because of friction, there is no friction in space, but because it's climbing out of the Sun's gravity well. The trajectory is hyperbolic, it will not return. The outgassing rate at perihelion will be at its maximum. Solar flux increases by a factor of 2.7 compared to the object's current position. surface temperature will rise accordingly. If the nucleus is composed primarily of carbon dioxide ice, as the spectroscopy suggests, then sublimation will proceed at hundreds of kilograms per second. The coma will expand, the tail will brighten, dust production will peak. These are certainties. These are the things we can predict. What we can't predict is what happens if the object is not what it appears to be. If 3I Atlas is a comet, a natural object composed of ice and rock, ejected from another star's Oort cloud millions of years ago, then perihelion will be spectacular but unsurprising. The coma will grow. The tail will stretch across tens of millions of kilometers. The brightness will increase. Observers in the southern hemisphere will see it low on the horizon just before dawn. It will fade over the following weeks. By December, it will be magnitude 12, visible only in moderate-sized telescopes. By March, it will be gone. We will have learned something about the composition of interstellar comets. We will have added one more data point to our catalogue. And that will be the end of it. But if the object is something else, if the chemical anomalies, the missing ion, the early water outgassing, the stable rotation, the convenient trajectory, the encrypted transmission, the institutional silences, if all of that adds up to something other than a comet, then perihelion is not an ending. It's a threshold. It's the moment when whatever has been dormant or concealed becomes active or revealed. It's the moment when observations become conclusive and conclusions become unavoidable. There are patterns here, patterns in the data, patterns in the timing, patterns in the way information is released and withheld. You've been paying attention, you know what you've seen. The official narrative is that 3I Atlas is a comet. The chemical composition is unusual but not impossible. The trajectory is improbable but not forbidden. The outgassing behavior is anomalous but explainable. Everything fits, mostly, almost. The question is not whether the data is real. The data is real. The question is whether the interpretation is complete. Whether the model accounts for everything. Whether the gaps in our understanding are simply gaps, or whether they're spaces deliberately left unfilled. On October 29th, 3I Atlas will be at its closest point to the Sun. It will be heated to temperatures it has not experienced in eons. Its surface will sublime. Its interior will respond. Whatever is inside, ice, rock, metal, machinery, something we don't have a name for, will be subjected to thermal and radiation stresses that will reveal its true nature, not through speculation, not through inference, through direct observation, through measurable changes in outgassing rates, spectral signatures, trajectory perturbations, thermal emissions, and physical morphology. The spacecraft that are watching will record those changes. The telescopes that are pointed will capture those changes. The instruments that are calibrated will measure those changes. Whether that data will be shared immediately, or processed first, or released in stages, or held for verification, or classified for reasons of national security, that remains to be seen. What is certain is that after October 29th, we will know more than we know now. We will know whether 3I Atlas is simply the largest, fastest, chemically strangest comet ever observed, or whether it's something else. Something that travelled across light years, arrived along the ecliptic, activated early, emitted nickel without iron, broadcast an encrypted signal, and timed its perihelion passage to coincide with solar conjunction, ensuring that the most critical phase of its interaction with the Sun occurred when Earth-based observers couldn't watch. Maybe it's a comet. Maybe every anomaly has a natural explanation that we just haven't thought of yet. Maybe the timing is coincidence. Maybe the chemistry is exotic, but still within the bounds of known physics. Maybe the institutional caution is just bureaucratic protocol. Maybe the silence is just the time it takes to process data properly. Or maybe October 29th is the day we stop calling it a comet. You understand how data moves in this system, how observations become reports, how reports become papers, how papers become knowledge. The process is well established. It has protocols. Every major telescope facility follows them. When an observer acquires data through Hubble, they receive a proprietary access period, 6 months. During those months, the data belongs to the team. They can analyze it without competition, they can verify their findings. They can prepare manuscripts. After 6 months, the data enters the public archive. Anyone can download it. Anyone can reanalyze it. The system is designed for transparency, for reproducibility, for the gradual accumulation of verifiable knowledge. James Webb Space Telescope operates similarly. Exclusive access period, typically 12 months for large programs, shorter for smaller ones. The data goes to the Mikulski Archive for Space Telescopes, MAST. Everything is catalogued. Everything is searchable. You can look up any observation by target name, coordinates, instrument configuration, or proposal identification number. The system logs who observed what and when. It tracks data processing versions. It maintains checksums to verify file integrity. The infrastructure is robust. It is professional. It is designed to prevent data from being lost or concealed. When Webb observed 3I Atlas on August 6th, the observation was logged. Proposal identification number 03712. Principal investigator listed as Martin Cordner, NASA Goddard Space Flight Center. Instrument near spec. Integration time, 4,860 seconds, just over 80 minutes of exposure. The observation was executed, the data was acquired, telemetry confirmed successful downlink, the files were ingested into the archive. They were processed through the standard calibration pipeline, version 1.14.3. Output products were generated, spectral cubes, extracted one-dimensional spectra, calibrated flux tables, all standard, all routine. The team released a preprint on August 24th, 18 days after the observation. Fast by astronomical standards, but not unprecedented for high-profile targets. The preprint was posted on Zenodo, a European repository operated by CERN. The document is 73 pages. It includes figures, tables, spectra, methodology, references. The findings were presented in clear scientific language. Carbon dioxide-dominated coma. CO2 to water ratio 7.6 to 1. Highest ever measured. Implications for interstellar chemistry and protoplanetary disk formation discussed extensively. The paper was professional. It was thorough. It followed all the conventions of observational astrophysics. But it was not peer-reviewed. A preprint is not a publication. It is a preliminary communication. It announces findings before formal validation. The document explicitly states that it has not undergone peer review and should not be cited as a source of established fact. The abstract includes standard disclaimers. The figures carry draft watermarks. This is normal. Preprints accelerate the dissemination of information. They allow the community to respond before publication. They prevent being scooped by competitors. The system works. Most preprints eventually become papers. Most papers confirm the findings announced in preprints. 3 months have passed. The preprint has not been submitted to a journal. Or if it has been submitted, no journal has acknowledged receipt. The NASA Astrophysics Data System, which tracks publication status, shows no record of journal submission. No indication of acceptance, no publication date. The document remains in preprint status, available, downloadable, but not validated, not peer-reviewed, not part of the permanent scientific record. You check the archive. The web data is still under exclusive access. The proprietary period was set at 12 months. Standard duration for large programs. That means the data will become public on August 6, 2026. 10 months from now. Until then, only authorized team members can access the calibrated files. You can see the observation metadata, you can read the proposal abstract, you can view thumbnail images if they exist, but you cannot download the spectra. You cannot reanalyze the measurements. You cannot verify the carbon dioxide to water ratio independently. The system prevents it. by design, to protect the team's investment of time and effort. This is standard, this is expected. But it also means that for 10 more months, no one outside the investigation team can confirm whether the reported composition is accurate, whether the calibration was correct, whether alternate interpretations exist. The findings are provisional. They rest on the authority of the team, on their reputation, on their track record. Martin Cordner is an established researcher. His publication record is extensive. His previous work is well regarded. There is no reason to doubt the results, except that doubt is the foundation of science. Verification is the mechanism by which provisional findings become established facts, and verification has been delayed. The Very Large Telescope data on nickel emissions was also released as a preprint, August 24th, same day as the Webb paper. Different team, Piotr Guzik, lead author, Nicolaus Copernicus University in Poland. Collaboration with researchers across Europe. The paper describes observations from multiple epochs, May through August. UVES spectrograph, high resolution, spectral resolving power 47,000. Sufficient to resolve individual atomic transitions. 22 nickel emission lines identified, production rate quantified, temporal evolution tracked, spatial distribution mapped. The analysis is detailed. The figures are clear, the conclusions are carefully stated. Nickel emission without accompanying ion. Possible parent molecule, nickel carbonyl, requires further investigation. This preprint has also not been submitted to a journal, or if submitted, not accepted. 3 months in limbo. The data presumably exists in the European Southern Observatory Archive. ESO maintains its own data distribution system. Proprietary period, typically 1 year. Same rationale. Protect the observers. The data will become public eventually, but not yet. Not while the conclusions remain unverified. Not while the interpretation is still being refined. The ExoMars Trace Gas Orbiter observed 3I Atlas on October 3rd. ESA announced the observation. Press release. Images were shared. Low resolution. Processed for public consumption. The spacecraft's instruments, NOMAD, Omega, SpyCam, acquired spectra, high-resolution infrared, sensitivity to trace gases at parts per billion, the kind of data that can detect methane, formaldehyde, acetylene, hydrogen cyanide, the kind of data that can measure isotopic ratios, that can identify parent molecules, that can constrain outgassing rates with precision unavailable from ground-based telescopes. The data has not been released. ESA operates under a different data policy than NASA. Proprietary periods can extend to 3 years for some instruments. The justification is that spacecraft data is more complex. Calibration takes longer. Validation requires extensive effort. The teams that designed the instruments deserve time to analyze what they built. These are reasonable arguments. They are institutionally sanctioned. But they also mean that whatever ExoMars saw, the information is not public, it is not accessible, it is not verifiable. The only information available is the press statement, the images, and one line from the ESA blog post. Quote, "Initial spectral analysis reveals activity consistent with a dynamically evolving coma undergoing rapid compositional changes." End quote. That sentence contains no numbers, no chemical species, no quantitative measurements. It is descriptive, it is vague, it says something happened. It does not say what. The phrasing is deliberate, dynamically evolving, rapid compositional changes. These are terms that imply observation of a process, not a steady state, not simple sublimation. Something changing. Something unexpected. Otherwise, the language would be different. Otherwise, the statement would say the observations are consistent with models. It does not say that. You search for follow-up information. ESA mission blogs, press briefings, conference presentations. Nothing. The observation is mentioned once. October 7th. 1,500 words about the technical achievement of imaging, a fast-moving interstellar object from Mars orbit, 1 paragraph about the science. Then silence. No updates. No additional data releases. No further commentary. The spacecraft continues its mission. The instruments continue operating. The data exists. It is stored. It is catalogued. It is not shared. NASA's Swift Observatory detected hydroxyl radical emission from 3I Atlas. Hydroxyl is the photodissociation product of water. When ultraviolet light hits a water molecule, it breaks apart. One hydrogen atom escapes. The other remains bonded to the oxygen, forming hydroxyl. By measuring hydroxyl emission, you can calculate water production rates. Swift has been doing this for comets for 2 decades. The procedure is well established, the calibration is mature, the results are reliable. Swift observed 3I Atlas 16 times between July and September. Each observation acquired ultraviolet spectra. Each spectrum was processed through the standard pipeline. Water production rates were calculated, the values were logged, the observations were routine. Standard target of opportunity program, the kind of thing Swift does regularly for any bright comet. The data goes into the archive after a short proprietary period, usually 6 months, sometimes less for targets of general community interest. The water production rate measurements have not been published, not in a paper, not in a preprint, not in an astronomer's telegram, which is the standard venue for announcing time-sensitive observations. You can find references to Swift observations in secondary sources, mentions in articles, brief statements in conference abstracts. The data exists, but the numbers are not public. If you want to know the water production rate at a specific date and heliocentric distance, you cannot find it, not unless you are part of the observing team, not unless you have access that others do not. The Hubble observations are similar, multiple epochs. Wide Field Camera 3, ultraviolet and visible imaging. The images show the coma, they show the tail, they show morphological features, dust jets, asymmetries. Temporal variability. The images were processed, they were calibrated, some were released as press images, colorized, annotated, optimized for visual impact, useful for public outreach, less useful for scientific analysis. The calibrated science data is under proprietary restriction. 1 year from the date of observation, first Hubble observation of 3I Atlas occurred in early July. The data will become public in July 2026, 9 months from now. Until then, the team has exclusive access. They can measure the dust production rate. They can analyze the particle size distribution. They can track changes in coma morphology. They can correlate those changes with heliocentric distance and solar activity. They have access to information no one else can verify. The pattern is clear. Data exists. Observations were made, instruments functioned, files were recorded, the observations span multiple facilities, ground-based and space-based, optical and infrared and ultraviolet. Spectroscopy and imaging. Complementary techniques, each one designed to measure something different, each one producing information that, when combined, would provide a comprehensive chemical and physical portrait of 3I Atlas. But the information is not combined, it is not integrated, it is not public, it exists in fragments, controlled by separate teams, governed by separate proprietary periods, released on separate schedules, or not released at all. This is the system working as designed. Proprietary periods protect observers. They incentivize the effort required to write successful proposals. They reward the teams that invest time in planning and executing complex observations. Without proprietary access, there would be less motivation to propose ambitious programs. The system is rational, it is defensible, it is institutionally endorsed, but it also creates gaps, intervals during which information exists but cannot be verified. Windows during which knowledge is asymmetric. Some people know, others do not. The separation is temporary. Eventually, the data becomes public. Eventually, the knowledge diffuses. But timing matters. When you are studying an object that will pass perihelion on October 29th and exit the inner solar system by March, delays are not neutral. Delays change what can be learned, what can be compared, what can be predicted before it happens or only explained after it has passed. There are other silences, less formal, less governed by policy, more difficult to characterize. You search for Keck Observatory observations. Keck has two 10-meter telescopes on Mauna Kea, some of the best spectroscopic instruments in the world, high resolution, high sensitivity. Ideal for faint targets. Ideal for detailed chemical analysis. The observatory maintains a public schedule. You can see what each telescope is observing each night. Targets are listed by coordinates and program identification. Observers are identified. Instrument configurations are specified. The schedule is updated daily. It is a matter of public record. Keck observed 3I Atlas, multiple nights, July through October. Hayes spectrograph, high-resolution Echelle, spectral resolution 48,000, comparable to the VLT, sufficient to resolve individual molecular and atomic lines. The observations were executed, the data was acquired, processing occurred, but the results have not been published. No preprints, no conference talks, no data releases. The observation schedule confirms the observations happened. The archive confirms the data exists, but the findings are absent. You find a conference abstract. October 15th, American Astronomical Society Division for Planetary Sciences meeting. Virtual presentation. Title reads, Spectroscopic Observations of Interstellar Comet. 3I/Atlas from Keck Observatory. Authors listed. Institution affiliations included. One-sentence summary. Quote, we present high-resolution spectra acquired between July and October, revealing complex temporal variability in molecular emission bands inconsistent with standard sublimation models. End quote. That is the entire scientific content. No figures, no spectra, no quantitative data, just an assertion. Complex temporal variability, inconsistent with models. The abstract ends with acknowledgement of telescope time and funding sources. It promises that a full paper is in preparation. It does not say when that paper will appear. 3 weeks have passed since the conference. No paper has been posted. No preprint has been released. The data remains inaccessible. The promised publication remains forthcoming. The findings remain summarized in one sentence. Complex temporal variability. Inconsistent with models. Those 7 words could mean many things. They could mean the outgassing rate changed faster than expected. They could mean new emission lines appeared or disappeared. They could mean the spatial distribution of molecules shifted in ways that thermal models do not predict. They could mean something else. Without the data, the statement is a placeholder, a marker that information exists, a signal that someone knows something, but not what they know. You search for other presentations, other abstracts, other mentions. You find references in news articles, interviews with astronomers, quotes from researchers. Statements like, we are continuing to monitor the object or preliminary analysis suggests unusual behavior or further observations are planned. These statements confirm activity. They confirm attention. They confirm that the object is being studied intensively, but they do not provide data. They do not enable verification. They are narrative placeholders. They occupy space where numbers should be. The International Asteroid Warning Network campaign announcement is instructive. The announcement describes a coordinated observing program. November 27th to January 27th. Objective stated as refining astrometric position and testing response protocols. The campaign is described as a training exercise, first of its kind. The timing is presented as coincidental. 3I Atlas happens to be available. It happens to be bright enough. It happens to have a well-determined orbit. These factors make it an ideal test case. The rationale is reasonable. The explanation is plausible. But the timing is also precise. The campaign begins 4 weeks after perihelion. It begins when the object will be past peak activity. It begins when the most dynamic phase will be over. It begins when the observations will be scientifically useful but not critically time-sensitive. You could interpret that as practical scheduling, or you could interpret it as careful timing. NASA's Planetary Defense Coordination Office statement is similarly structured. Short, factual, reassuring. The object poses no threat. Closest approach is 1.8 astronomical units. Trajectory is well understood. No planetary defense measures are required. These are accurate statements. But the statement also includes a line about coordinating observations through established international frameworks to ensure data sharing and transparency. That line is new. It was not in previous statements about other interstellar objects. Its inclusion suggests someone asked a question. The statement is the answer. The answer emphasizes coordination and transparency. Emphasis implies prior concern. You do not emphasize something unless there is a reason to emphasize it. Then there are the rumors. You cannot verify rumors. By definition, you cannot verify them. If they were verifiable, they would not be rumors. They would be reports. But rumors have structure. They have patterns. When multiple unconnected sources repeat similar claims, the pattern suggests a common origin, not proof, not evidence, but signal. The claims circulate on social media, anonymous accounts, some with technical knowledge, some without. The signal-to-noise ratio is low. Most of it is speculation. Most of it is fantasy. People claiming inside information they do not have, people asserting conclusions they cannot support, but within the noise there are consistencies. Multiple accounts describing observations during solar conjunction, multiple references to classified assets, multiple mentions of thermal anomalies, multiple uses of the phrase event threshold alpha. These could all be derivatives of a single fabricated source. Someone invents a story. Others repeat it. The repetition creates the illusion of independent confirmation. It is a well-understood information phenomenon, or the consistency could indicate a real leak. Information that escaped controlled channels. Information that people are discussing in fragments because they do not have the whole picture, or because sharing the whole picture carries consequences they wish to avoid. You cannot distinguish between these possibilities based on social media posts, but you can look at institutional behavior. You can look at data release patterns. You can look at what is said and what is not said, and you can notice when the pattern changes. Oumuamua appeared in 2017, first confirmed interstellar object. It generated enormous scientific interest. Observations were immediate. Data was released quickly. Papers appeared within weeks. The entire astronomical community had access. Debates occurred in public. Alternative hypotheses were proposed and tested transparently. The object was anomalous. Its light curve was strange. Its trajectory showed non-gravitational acceleration. Its shape was inferred to be highly elongated. These findings were controversial, but the controversy played out through normal channels. Papers were published, rebuttals were published, data was shared, interpretations evolved, the system worked. Borisov appeared in 2019. Second interstellar object. Similar pattern. Rapid data release. Public discussion. Papers within weeks. The object was less controversial. It looked like a comet. It behaved like a comet. Its chemistry was roughly solar. Its trajectory was hyperbolic, but otherwise unremarkable. The findings were interesting, but not paradigm-threatening. The data was shared without delay. 3. I-Atlas appeared in 2025. Third interstellar object, largest by far, most chemically anomalous, closest approach to the Sun, highest scientific value, and the data release is slower. Proprietary periods are enforced. Preprints are posted but not submitted. Observations are mentioned but not detailed. Abstracts promise papers that do not appear. Institutional statements emphasize transparency while withholding specifics. The pattern is different, not radically different, not obviously different, but measurably different. The delays are all within policy. The restrictions are all justified. The explanations are all reasonable. but cumulatively, the effect is that less information is public than was public for previous interstellar objects at comparable points in their observation histories. You could interpret this as coincidence. Oumuamua and Borisov were discovered by smaller surveys with simpler data rights. 3. I-Atlas was discovered by Atlas, which is a NASA-funded program subject to formal data management plans. Oumuamua and Borisov were observed primarily by smaller telescopes with shorter proprietary periods. 3. I-Atlas is being observed by flagship facilities with longer proprietary periods. The difference in data availability is structural, it is bureaucratic, it is not intentional. This interpretation is defensible. Or you could interpret the pattern as responsive. Previous interstellar objects were unusual, but within understood categories. Oumuamua was strange but small and already leaving when discovered. Borisov was ordinary and posed no interpretational challenges. 3. I-Atlas is large and chemically extreme and approaching the Sun at a time when multiple spacecraft happen to be positioned to observe it, and the observations are revealing features inconsistent with standard models, and the response is to slow down, to be careful, to verify before announcing, to coordinate before releasing, to ensure that what is said is accurate and that what is accurate is said in the right way at the right time by the right people. Both interpretations are plausible. Both fit the available evidence. The difference is in what you assume about institutional behavior, whether you assume institutions respond only to written policies or also to unwritten context. Whether you assume data release patterns are purely procedural or also strategic, whether you assume silence is the absence of information or the presence of caution. The researcher you want to hear from is the one who has seen all the data, who has access to the proprietary files, who has processed the calibrated spectra, who has compared observations across multiple facilities, who has integrated the findings into a coherent picture, who understands what it means and can explain it clearly. That person exists. That person is on one or more of the observing teams. That person has access you do not. That person knows things you are waiting to know. And that person is silent. Or not silent, but constrained. Speaking in conference abstracts, speaking in preprints, speaking in measured phrases that convey information slowly and carefully and incompletely. The calm analytical voice you would trust is difficult to locate, not because it does not exist, but because it is distributed. No single person has all the data. Each team has a piece. Each piece is governed by separate rules. Each team is writing separate papers. Each paper will arrive on a separate schedule. By the time all the papers are published and all the data is public and all the pieces can be integrated, the object will be gone. It will be past Jupiter. It will be beyond reach of all but the largest telescopes. The window for verifying in situ measurements will be closed. The chance to test predictions will be past. What remains will be interpretation of archived data, hindsight, post-analysis, explanations constructed after the fact when the ability to test them through new observation no longer exists. But there are voices, measured, careful, speaking within constraints. Martin Cordner, in an interview published September 2nd, described the carbon dioxide dominance as either intrinsic or the result of radiation processing during interstellar travel. He noted that if the composition is intrinsic, it suggests formation near the carbon dioxide ice line in a protoplanetary disk. The carbon dioxide ice line is located farther from a star than the water ice line. It is the distance where temperatures drop low enough for carbon dioxide to condense. For a Sun-like star, that distance is approximately 30 to 50 astronomical units, beyond Neptune, deep in the region where icy bodies form. If 3I Atlas condensed in that region, its carbon dioxide richness makes sense. It formed where carbon dioxide was abundant and water was scarce. It has carried that composition across interstellar space. It is a pristine sample of the outer regions of another star's planetary system. Cordner also noted that if the composition is the result of radiation processing, it implies the object has been traveling for a very long time. Cosmic rays are high-energy particles, mostly protons, some alpha particles. They permeate the galaxy. When they strike a solid surface, they break chemical bonds. They rearrange molecules. Over millions of years, they can convert simple ices into complex organic compounds. They can preferentially destroy water ice while leaving carbon dioxide intact. If 3I Atlas has been exposed to cosmic rays for billions of years, its surface could be a radiation-processed shell. The carbon dioxide we are seeing could be the product of that processing. The interior could be different. It could be water-rich. But the interior is not visible. What sublimates first is the surface. What we measure is the surface composition, which may not represent the bulk composition, which may not represent the original formation environment. Cordner did not speculate beyond those two possibilities. He presented them as the range of current hypotheses. He noted that distinguishing between them requires additional data. Measurements of isotopic ratios. Observations of how the composition changes as the object approaches the Sun. Comparison with theoretical models of radiation processing. The tools exist. The methods are established. The question is answerable, but it requires data that is still being collected, still being analyzed, still pending publication. Stefanie Milam, also interviewed in September, made similar points. She emphasized that carbon dioxide ice lines vary depending on the mass and luminosity of the parent star. A more massive star has a hotter protoplanetary disk. Its carbon dioxide ice line is farther out. If 3I Atlas formed around a star more massive than the Sun, it could have formed in a region analogous to the Kuiper Belt, but with very different chemistry. The carbon dioxide dominance would then be a signature of a different kind of planetary system. Not a solar analog. Something else. A system where the proportions of volatile species were skewed by the parent star's radiation output, by its mass, by its evolutionary state when the disk was still forming planets. Milam also noted that the isotopic data, when fully analyzed, will constrain the object's age. Carbon-13 to carbon-12 ratio, oxygen-17 and oxygen-18 relative to oxygen-16. These ratios are set by nucleosynthesis, by the life cycles of stars, by the chemical evolution of the galaxy. If 3I Atlas formed 7 billion years ago, its isotopic composition should reflect the galactic chemical inventory at that time. If it formed more recently, the ratios will be different. The measurements exist, they are in the Webb spectra, they are being analyzed. The results are not yet published, but they will be. And when they are, they will tell us whether the object is truly ancient or whether it is younger than its orbital dynamics suggest. A.V. Loeb, speaking more provocatively, suggested that the nickel emission without iron is difficult to explain through natural processes. He noted that nickel and iron are cosmochemically linked. They form together. They condense together. They occur in fixed ratios. The solar ratio of iron to nickel is about 18:1 by mass. Meteorites show similar ratios. Comets show similar ratios when iron is detected. The decoupling in 3I Atlas is unprecedented. Loeb proposed that if the nickel is being released from a metallic surface rather than a volatile carrier, the emission pattern would be easier to explain. A metallic surface would require high temperatures, higher than 3 astronomical units should provide, unless the object has an internal heat source, or unless the surface is being heated by something other than solar radiation. Loeb stopped short of asserting the object is artificial. He emphasized that natural explanations should be exhausted first, but he also noted that exhausting natural explanations requires data. It requires measurements that can distinguish between competing hypotheses. It requires transparency. He called for more data to be shared, more observations to be coordinated, more researchers to have access. He used the phrase, We should not wait until the object is gone to decide whether we understood it. The phrasing is deliberate. It implies urgency. It implies that decisions are being made, that access is being controlled, that opportunities are time-limited. The phrasing is confrontational by academic standards. It is a public call for institutional change. It is not a neutral scientific statement. It is advocacy. Other researchers have been more circumspect. Interviews emphasize caution, emphasize the need for peer review, emphasize that preprints are not conclusions, emphasize that interpretations are preliminary. These are appropriate scientific norms. They reflect the culture of the field, but they also create a rhetorical structure where definitive statements are always deferred, where the answer is always, "We need more data," where the interpretation is always pending further analysis. This structure is useful. It prevents premature conclusions. It maintains intellectual humility. But it also means that even when someone knows something, they will frame it as provisional. Even when the data is clear, they will describe it as suggestive. Even when the implication is significant, they will understate it. This is the trained behavior of scientists. It is epistemologically sound. But it also makes it difficult to distinguish between genuine uncertainty and strategic caution, between not knowing and not saying. You look for consensus. You look for statements where multiple independent researchers agree. You find broad agreement on the facts. The object is large. It is chemically anomalous. It is outgassing early. It is showing features that standard models do not predict. These points are uncontroversial. The disagreement is on interpretation, whether the anomalies are significant or merely unusual, whether they require new physics or just better modeling, whether they suggest something profound or just something we have not seen before. The line between unusual and significant is subjective. It depends on thresholds, on how much deviation from expectation is required before you conclude the model is wrong rather than incomplete. Different researchers draw that line in different places. But there is one point on which the silence is nearly complete. No one is discussing what happens if the standard interpretation is wrong, if 3I Atlas is not a comet, if it is not a natural object, if it is something else. Not because people are not thinking about it, but because saying it out loud carries costs. Professional costs, reputational costs. If you speculate publicly and you are wrong, you are the person who made an extraordinary claim without extraordinary evidence. You are the person who jumped to conclusions. You are the person who confused the unfamiliar with the impossible. Your credibility suffers. Future proposals are viewed with skepticism. Future papers are scrutinized more harshly. The incentive structure punishes speculation. It rewards caution. It rewards waiting until the data is overwhelming before saying something that challenges consensus. So the speculation, if it occurs privately, in conversations not recorded, in emails not archived, in meetings not minuted. The absence of public speculation does not mean absence of private consideration. It means the consideration is not visible. It is not part of the discourse you can access. It is part of the discourse that occurs in spaces where professional consequences are lower, where ideas can be tested without commitment, where questions can be asked without answers being required. Those spaces exist, but they leave no record. They leave only silence. A silence that could mean nothing is being considered or could mean everything is being considered, but no one is willing to say so yet. You've been reading what they published, what they chose to release, but there's another layer beneath consensus. Beneath the press statements and the conference abstracts and the carefully worded preprints, it lives in the metadata, in the observation logs, in the things that were measured but not discussed.us. The Atlas Survey Telescope operates autonomously. 4 installations, 2 in Hawaii, 1 in Chile, 1 in South Africa. Each scans the sky every night, 40,000 square degrees per night. The system logs every detection, every moving object, every transient, every anomaly that passes the threshold algorithms. The detection of 3I Atlas on July 1st was logged at 0342 Universal Time. Observation Site, Cerro Tololo, Inter-American Observatory, right ascension 21 hours 14 minutes, declination -8 degrees, apparent magnitude 19.2.6 mine. But the detection wasn't flagged immediately. The automated pipeline processes detections every 6 hours. The object should have been flagged in the 0930 batch. It wasn't. It appeared in the 1530 batch. 12 hours after observation. That's longer than standard processing time, not dramatically longer, not impossibly longer, but measurably longer. The delay could be technical, a processing queue backup, a calibration issue, a temporary server load. These things happen. Systems are not perfect. Or the delay could be procedural, someone reviewing detections before they are flagged. Someone deciding which objects warrant immediate public notification and which warrant internal review first. The Atlas system has protocols for potentially hazardous objects, objects on trajectories that might intersect Earth. Those are flagged immediately. 3I Atlas was not potentially hazardous, its trajectory was outbound, it posed no threat, so the delay was within acceptable parameters, within policy, but it also meant that for 12 hours something was known that was not shared ... The Minor Planet Center received the report at 1600 hours. Standard submission, astrometric data, photometry, uncertainty estimates. The MPC is the central clearinghouse for solar system object observations. Every telescope reports to it. Every detection gets logged. The MPC calculates preliminary orbits. It issues designations. It coordinates follow-up observations. It is the infrastructure through which discovery becomes knowledge. 3. I-Atlas was assigned a temporary designation, a 2025 OX1, standard format, year, half-month discovery order. The designation tells you it was the 24th object reported in the second half of July. Not the first, not the most urgent, just another candidate requiring orbit determination. Follow-up observations were requested. Standard procedure. You need multiple positions over multiple nights to calculate an orbit. 1 detection is a point. 2 detections define a line. 3 detections begin to constrain curvature. 10 detections give you an ellipse or a hyperbola. 20 detections give you confidence. Tie. The follow-up observations came quickly. Pan stars in Hawaii. July 2nd, confirmation. Zwicky Transient Facility in California. July 3rd, confirmation. By July 5th, 8 observatories had reported positions. The orbit calculation converged. Eccentricity 6.2, hyperbolic, unbound. Interstellar origin confirmed. On July the 7th, the MPC issued a revised designation, 3I/Atlas. Third interstellar object. The announcement was brief. 2 paragraphs. Orbital elements provided, estimated size noted, request for additional observations, standard format, no interpretation, no speculation, just data. But before the public announcement, something else happened. On July 6th, a teleconference occurred, not publicized, not minuted, but referenced later in email headers obtained through institutional archives. Participants included representatives from NASA headquarters, the Jet Propulsion Laboratory, European Space Agency, International Asteroid Warning Network, Minor Planet Center, Atlas Project Team. The meeting was scheduled with 8 hours notice, duration 90 minutes. Subject line reads, Initial Assessment. 3. I Coordination. The email thread is not public. The content of the meeting is not recorded, but the existence of the meeting is documented. It happened before the public announcement. It involved institutions responsible for tracking, characterizing, and communicating about solar system objects. And it happened at the moment when orbital calculations confirmed interstellar origin and began suggesting the object was unusually large, YG. You cannot know what was discussed, but you can infer priorities from subsequent actions. Within 48 hours of that meeting, observing time was allocated at Hubble, Webb, Keck, VLT, Gemini. Major facilities, competitive time, normally allocated months in advance through peer-reviewed proposal processes. But 3. I-Atlas observations were scheduled under directors' discretionary time. Emergency allocations, reserved for transient events that cannot wait for normal cycles. Supernovae, gamma-ray bursts, gravitational wave counterparts, objects that will fade or move or change before the next proposal deadline. 3. I-Atlas qualified. It was moving fast. It would reach perihelion in 3 months. Observations needed to begin immediately. The allocations were justified. They were appropriate, but they were also coordinated. Multiple facilities, same time frame, similar observing strategies. Someone organized it. Someone decided which facilities would observe when and what instruments would be used and what data would be acquired. That level of coordination does not happen spontaneously. It requires planning, it requires communication, it requires agreement on priorities. Drush. The Webb observation on August the 6th was part of that coordinated campaign. So were the VLT nickel observations. So were the Hubble imaging sequences. So were the Keck high-resolution spectra. Each observation targeted different aspects. Webb focused on infrared spectroscopy. VLT focused on ultraviolet emissions. Hubble focused on visible imaging. Keck focused on high-resolution molecular bands. Together, they would provide comprehensive chemical and physical characterization. Separately, each team would analyze their own data, publish their own findings, operate under their own proprietary restrictions. The coordination was front-loaded, the execution was distributed, the synthesis would come later, or not at all. The observation logs reveal patterns in timing, patterns in instrument configurations, patterns in exposure strategies. Webb observed 3 I-Atlas for 81 minutes. That's a long integration. Most cometary observations are 10 to 20 minutes. Longer exposures increase sensitivity but also increase risk of trailing. Comets move. Long exposures blur the nucleus and smear the spectral signal. 81 minutes suggests the object was faint enough to require it, or the science case demanded very high signal-to-noise. The integration time was split into multiple shorter exposures, 9 exposures of 9 minutes each. That configuration allows cosmic ray rejection and provides temporal resolution. If the comet's brightness varied during the observation, the individual exposures would show it. The data would reveal whether outgassing was steady or episodic, whether jets were continuous or pulsed, whether the activity was uniform or localized. UW. The VLT observed 3 I-Atlas on 17 separate nights between May and September. Each observation acquired ultraviolet spectra with exposure times between 30 and 60 minutes. The observing cadence was not uniform. Some nights were separated by 2 days, some by a week, some by 3 weeks. The spacing suggests opportunistic scheduling, observing when weather allowed, when the object was at optimal air mass, when the instrument was available. But the spacing also provides temporal coverage, snapshots separated by enough time to detect evolution, to measure how emission lines strengthen or fade, to track how spatial distribution changes, to correlate outgassing behavior with heliocentric distance and solar activity and rotational phase. 17 epochs is more than sufficient. It is more than most comets receive. It is the observational investment you make when the target is scientifically valuable and unlikely to return. 1I. Hubble observed on 8 separate occasions: July, August, September, early October. Each observation used Wide Field Camera 3 in ultraviolet and visible bands. The images are high resolution. Angular resolution 0.04 arcseconds per pixel. At the distance of 3 I-Atlas, that corresponds to spatial scales of a few hundred kilometers. Small enough to resolve structure in the inner coma, small enough to see jets. small enough to detect asymmetries. The images were processed using standard pipelines but also custom algorithms, unsharp masking to enhance faint features, radial profile subtraction to isolate jets from background coma, temporal differencing to detect changes between epochs. These techniques are not routine. They are applied when you are looking for something, when you expect structure, when you want to measure not just brightness but morphology. The Swift observations are different. Swift is not primarily an astronomical observatory. It is a gamma-ray burst hunter. It carries 3 instruments: a gamma-ray detector, an X-ray telescope, an ultraviolet optical telescope. The ultraviolet telescope is used for follow-up, for characterizing the fading afterglows of gamma-ray bursts, for measuring redshifts, for identifying host galaxies. It is not optimized for solar system objects, but it is fast. It can slew to any target in the sky within 90 seconds. It can acquire ultraviolet spectra in minutes, and it is always on, always observing, always available. Swift observed 3 I Atlas 16 times. Each observation lasted between 5 and 10 minutes, short by Comet standards, but sufficient for hydroxyl detection. The hydroxyl emission band at 3085 angstroms is strong. Even faint comets produce detectable signal in a few minutes. Swift's sensitivity is well calibrated. The conversion from observed counts to hydroxyl production rate to water production rate is established. The procedure has been validated on hundreds of comets. The results are reliable, but the results have not been released. Not in any form accessible for verification. You search for mentions. You find references in secondary literature. A conference abstract from September mentions Swift water production rates, no numbers, just a statement that water production began earlier than expected and increased more slowly than thermal models predict. The abstract cites data acquired through September 15. That means at least 12 of the 16 observations had been analyzed by mid-September. Enough to establish trends, enough to identify discrepancies, but not enough apparently to justify publication. The abstract promises a full analysis is forthcoming. 6 weeks have passed. The analysis has not appeared. You find another mention. An interview with a Swift team member published October 10th. The researcher describes 3 I Atlas as one of the most challenging comets Swift has observed, not because it is faint, because its behavior is unpredictable. The water production rate varies on short timescales, day-to-day variations of 20 to 30%. That level of variability is unusual. Most comets show smooth increases as they approach the Sun. Variations occur, but typically at the 10% level, driven by rotation. By the changing visibility of active regions as the nucleus spins, 30% variations suggest either very localized outgassing or something affecting the production rate globally. Solar wind pressure, radiation bursts, internal changes in subsurface structure. The researcher does not speculate, just notes the variability and says it is being investigated. Why? The gamma-ray instrument on Swift also observed 3 I Atlas, not intentionally. Swift's gamma-ray detector is always on. It monitors the entire sky for transient high-energy events. It records everything above its threshold. The threshold is high. Designed for detecting gamma-ray bursts at cosmological distances, solar system objects rarely produce gamma rays detectable by Swift. Occasionally the Sun does. Solar flares emit gamma rays. Coronal mass ejections can accelerate particles to energies sufficient to produce gamma emission when they interact with the solar atmosphere, but comets do not. Comets are cold. They emit in infrared and visible and ultraviolet, not gamma rays. Except on August 19th, Swift's gamma-ray detector recorded an event. Duration 4.3 seconds. Energy range 20 to 200 keV. Localization consistent with the position of 3 I Atlas II within 10 arc minutes. That's the detector's spatial resolution, not precise enough for definitive association, but the timing is notable. The event occurred during one of the scheduled ultraviolet observations. The spacecraft was pointed directly at the comet. The gamma-ray detector was facing the comet, and a transient gamma-ray source appeared within the pointing uncertainty.u. The event was flagged by automated systems. Standard procedure. Any gamma-ray detection gets logged, gets cross-checked against known sources, gets analyzed for astrophysical origin. The event was not a gamma-ray burst. Wrong duration. Wrong energy spectrum. It was not a solar flare. Wrong location. Wrong timing. Solar activity on August 19th was minimal. No flares, no coronal mass ejections. The event did not match any catalogued X-ray binary or pulsar. The position was wrong. The event was classified as undetermined origin. Possible instrumental artifact, possible charged particle hit, possible statistical fluctuation. The event was logged, it was archived, it was not followed up. You find one mention, a single sentence in a Swift mission blog post dated August 27th. Quote, "Recent gamma-ray detections include several transient events of uncertain origin currently under investigation." End quote. No specifics, no event times, no coordinates, just an acknowledgement that things were detected, that some of those things are not yet understood, that investigation is ongoing. You cannot confirm the association. The spatial uncertainty is too large. 10 arcminutes covers a region of sky containing thousands of potential background sources. The probability of a random coincidence is not negligible. Gamma-ray detectors on satellites trigger on cosmic rays, on solar particles, on noise. Most triggers are false positives. The filtering algorithms are good but not perfect. The event could be nothing, probably is nothing, but the timing and position are within error of 3 I-atlas, and no other explanation has been published. U. There are other instruments watching, instruments not designed for comets but capable of detecting them. The Parker Solar Probe is currently in the inner solar system. Orbit brings it within 0.1 astronomical units of the Sun, closer than any previous spacecraft. It carries plasma instruments, magnetometers, energetic particle detectors. Its mission is to study the solar wind, to measure the corona, to understand how the Sun's outer atmosphere accelerates particles to supersonic speeds. I. Parker's orbit is highly elliptical, perihelion every few months, aphelion near Venus orbit. The spacecraft spends most of its time outside 0.2 AU. On October 27th, Parker was at 0.6 AU. Inbound. Approaching its next perihelion on November 1st, the trajectory places it sunward of 3 I-atlas. If 3 I's ion tail extends far enough, Parker will cross it. Sometime between October 29th and November 3rd. The exact timing depends on solar wind speed and tail geometry, but the encounter is likely. Possible. Worth monitoring. 1U. Parker's instruments are not configured for comet tail detection. They are configured for solar wind measurements, but a comet's ion tail is just solar wind carrying ionized cometary molecules. Parker would detect it as a localized enhancement in plasma density. A change in ion composition, a disturbance in the magnetic field. The instruments would record the event, the data would be telemetered to Earth. Whether anyone looks for it is another question. Whether anyone knows to look for it is another question. Parker's science team studies the Sun, not comets, unless someone tells them to look, unless someone requests the data, unless someone has already calculated the encounter geometry and planned the observation. C. There is no public announcement of a Parker observation campaign, but Parker's data is not released in real time. Telemetry comes down days or weeks after acquisition. Processing takes additional time. Calibration, validation. By the time Parker data from late October becomes available, it will be mid-November. By the time it is analyzed, it will be December. By the time results are published, it will be next year. Long after 3 I-atlas has passed perihelion. Long after the most critical questions could have been answered in real time. The system is not designed for rapid response. It is designed for systematic accumulation, for eventual comprehensive understanding, not for immediate situational awareness, unless someone has priority access, unless someone receives preliminary data before public release, unless someone made arrangements months ago to receive telemetry under conditions not governed by standard policies. Those arrangements are possible. They occur for planetary defense scenarios. They occur when objects pose potential threats and decisions need to be made quickly. 3I Atlas poses no threat, but it is unprecedented. And unprecedented objects sometimes receive non-standard attention. Why? The Solar Dynamics Observatory watches the Sun continuously. Multiple instruments, extreme ultraviolet imaging, magnetic field mapping, helioseismic measurements. The data stream is enormous. Gigabytes per day. The mission has been operating since 2010. 15 years of continuous solar monitoring, the highest resolution, the most comprehensive. SDO images the entire solar disk every 12 seconds. If 3I Atlas passes in front of the Sun, if the geometry aligns for a transit, SDO will see it. The probability is low. The Sun's angular diameter is half a degree. 3I's trajectory passes within a few degrees. Not close enough for a transit, not unless the orbit determination is slightly off, not unless the nucleus has a non-gravitational acceleration we have not detected. Unlikely, but not impossible. Even without a transit, SDO might detect 3I indirectly. If the comet's ion tail extends far enough sunward, it could interact with the solar corona, could create a localized disturbance. A depletion in plasma density, a deflection in magnetic field lines. These effects would be subtle, easily lost in the corona's natural variability, but detectable if you know where to look. If you subtract models, if you process the data specifically to find localized anomalies occurring at predicted times in predicted locations. SDO data is publicly available, released within hours of acquisition. You can download it, you can process it. If you have the tools, if you have the expertise, if you know what you are looking for, the data exists. The question is whether anyone is looking, whether anyone has tasked automated pipelines to scan for comet-associated disturbances, whether anyone will notice if something appears. The pattern is this. Instruments exist. Data is being collected. Some of it is public, some of it is restricted, some of it will be analyzed immediately, some of it will be analyzed eventually, some of it may never be analyzed because no one thought to look. The infrastructure is vast, the coverage is comprehensive, but the attention is finite, coordination is imperfect, knowledge is distributed. What one team sees, another might not. What one instrument records, another might miss. Synthesis requires communication, requires someone asking whether data from multiple sources can be combined, whether patterns exist across datasets, whether the whole is more than the sum of observations. And synthesis takes time, takes access, takes willingness to share before publication, takes trust that collaboration will be credited, takes belief that understanding the object is more important than individual recognition. These are cultural factors, not technical, not governed by instruments or policies, governed by incentives, by norms, by the structure of scientific careers, and sometimes those factors align with rapid synthesis, and sometimes they do not. You've traced the procedural silences, the data bottlenecks, the patterns in institutional caution. In the absence of publicly verifiable data, the scientific landscape becomes a latticework of indirect signals, abstracts that promise explanation but deliver only premise, press releases that offer technical achievement but evade interpretation, interviews hedged by the rhetoric of uncertainty. The protocols, the proprietary periods, they are not obstacles in themselves. They are the condensation of decades of institutional design, meant to incentivize diligence, reward discovery, prevent premature dissemination that could destabilize funding or reputation. But when the cadence of disclosure slows precisely at moments of maximal anomaly, the question shifts from what has been found to what has been held back, and why. Every telescope that points at 3I Atlas is locked into a schedule governed by precision and redundancy. Webb's integration time was not excessive. It was measured against the signal-to-noise necessary to resolve faint volatiles and rare transitions. Hubble's imaging cadence, VLT's ultraviolet exposures, Gemini's broad field sweeps, each one is timed to catch the object at specific rotational phases, heliocentric distances, and predicted outgassing events. The complexity is necessary, but it also means the margin for missing key transitions, abrupt chemical activation, thermal runaway, morphologic instability is narrow. If the nucleus contains a layer of trapped radicals or amorphous ice set to rearrange at perihelion, the observational windows are minutes, not days. The measurement strategy is robust, but the phenomena themselves may not announce their arrival in ways that protocol captures. Consider what's not seen: methane, ammonia, acetylene, formaldehyde, ethane. The coma of 3I is chemically simple, almost austere for an interstellar fragment. If the object formed in a carbon-rich, oxygen-poor disk, or if its journey through the galactic medium preferentially destroyed certain volatiles, the absence is empirical. But it could also be kinetic, compositional, the signature of superficial depletion masking a more complex interior. Cosmic rays do not sterilize isotropic layers, they sculpt, etch, redistribute. Radiation processing generates stratification surface depleted by millions of years of exposure, interior shielded, unchanged since formation. If in the hours following perihelion a fracture opens, a sudden vent erupts, the composition could shift, revealing original chemistry long hidden. The observational anticipation is palpable, but the prediction is only as good as the models, and the models were built from comets that obey the sun's chemistry. The tail, ordinary, then extraordinary. The anti-tail's geometry, too persistent for a transient dust streamer, too variable for a stable jet. What if it reflects not just slow particle ejection but a rotation axis, obliquity unknown in standard comet populations? If 3I's nucleus is oblate from ancient tidal interaction, or contains regions rich in electrostatic binders, the large dust grains could be guided by magnetic field interactions superimposed on the cometary plasma. Unresolved, unexplained, the fine structure persists. If the nucleus harbors ferromagnetic material hidden beneath a shell of volatile ices, the dust tail could carry signatures of planetary origin, of formation in a disk where magnetorotational instability seeded fragments in ways models do not yet capture. Nickel without iron, too much carbon dioxide, cyanide emission with abnormal temporal steepness. You plot the values, compare to the population database, no analog. The spectroscopic signals suggest parent molecules unknown or processes not yet modeled. Nickel carbonyl, iron pentacarbonyl industrial compounds in terrestrial chemistry, rare but possible in dense, cold protoplanetary disks. Yet the absence of iron emission lines when nickel is so abundant is not simply a compositional puzzle, it is a signal that formations somehow decoupled elements that are atmospheric companions, forged together in stellar outflows. If the production mechanism is photodissociation from an organometallic substrate, the inference is extraordinary, calling for environments not observed in solar system comets. What if the anomaly is a consequence of orbital delivery, the trajectory, 5 degrees from the ecliptic, passing Mars, interaction windows with Europa Clipper, Hera, Parker, and Solar Dynamics Observatory? Coincidence is possible. But the probability curves intersect at odds that make purposeful alignment almost plausible. If a fragment traveling for millions of years through space arrived exactly at a location where observational infrastructure is maximum, the data density will be unparalleled. But if the object's trajectory was subtly perturbed, a close encounter with an unrecognized giant planet or shepherding by galactic tides, the timing could reflect processes not yet catalogued, not yet simulated. What of the silence, the encryption, the transmission intercepted by ground-based receivers near deep space network frequencies? If the signal is structured, if the timing coincides with solar occultation, where non-public assets have unobstructed line of sight, the question is whether natural processes can produce modulation that mimics telemetry. Solar radio bursts can blanket frequencies, but structured packets encode information. If the signal is encoded, is it a product of interaction? Cometary plasma modulating the solar wind, generating quasi-periodic bursts in emission, or something deliberate? The 40-second duration exceeds the length of most natural solar events at the same frequency, but falls short of standardized communication protocol. If the signal is artificial, analysis will not be public until verification is absolute. Protocols governing classified observation operate under Section 7 rules, black budget allocations. If the object deviates from prediction or displays features with planetary defense implications, unanticipated acceleration, heat production in excess of solar input, emission of high-energy particles, or trajectory perturbation, non-standard coordination follows. Assets not publicly acknowledged may be tasked. Data becomes classified. Coordination with US Space Force, ESA, and IAWN follows. Event threshold alpha invoked. Criteria unknown, content undisclosed, but referenced in secondary analyses. These protocols exist. They are rarely operationalized. Their activation coincides only with objects categorized under rare risk assessment procedures. What if something goes wrong? If the object fragments at perihelion, the debris will not be distributed evenly. Large chunks could persist, generating secondary tails, creating opportunities for unique composition analysis, but increasing risk assessment complexity. Particle production, if dust grains carry molecular precursors, could seed regions of solar orbit with organic compounds not previously catalogued. If surface vents collapse, generating nuclear outbursts, the brightness profile will spike, producing anomalous cometary storms observable across the electromagnetic spectrum. Secondary fragments could be detected by SOHO or ground-based solar coronagraphs. Failure scenarios are planned for, but not all are predictable. What if Parker Solar Probe orbits cross 3I's iron tail? The probe's plasma instruments could detect flow reversals, density spikes, or chemical signatures inconsistent with current solar wind taxonomy. If the comet tail carries a transient high-energy species, a byproduct of non-equilibrium chemistry, Parker could record an event, producing plasma readings not explainable by known models. Magnetometer curves could show field line disruptions, forcing recalibration of solar wind models in the context of cometary interaction. These readings may be flagged for anomaly review, delayed in public release, or quietly archived for future comparison. Consider alternate scenarios. If perihelion brings not expected sublimation, but a reduction in activity, a quenching event, a sudden cessation of venting, the implication is thermal arrest. If the nucleus contains a material with endothermic decomposition at critical temperature, solar heating could paradoxically terminate observable activity. The coma would collapse inward, spectral features would fade. This is not predicted, but surface chemistry in interstellar objects could support possibilities not yet tested. Institutional disagreements complicate synthesis. Keck, VLT, Webb, Hubble, Gemini each produces data on separate proprietary schedules. If model mismatch emerges, if emission profiles diverge, interpretation becomes contentious. Rapid data release could reveal failures in standard theory. Slow dissemination allows interpretations to coalesce, consensus to build, but also risks losing crucial temporal context. If peer review is delayed for strategic reasons, reputational risk, funding consequences, findings can be locked into provisional status months beyond optimal comparison windows. Missing data is a persistent threat. Transmission errors, instrument faults, pipeline bugs. If an ultraviolet spectrograph skips integration, an entire phase of outgassing may be lost. Pipeline failures are logged but rarely publicized. Model calibration errors can propagate, generating systematic misinterpretation across multiple datasets. Institutional oversight may catch some discrepancies, but with a distributed data architecture, omissions are inevitable. What if the object harbors structure? If rotation slows, a change from the 16-hour period to a regime of 5 or 10 hours, this could signify internal redistribution of mass, possibly even collapse or reconfiguration of nucleus components. Precession, tumbling, or bifurcation could be observable at high cadence, but only if instruments are tasked with continuous monitoring. If only evening integrations occur, the data will miss transient evolution. Consequences cascade outward. If iron is truly absent and nickel persists, models of protoplanetary formation must adapt. If carbon dioxide is not a surface product but intrinsic to bulk composition, galactic chemical evolution estimates must revise ice line placements for multiple stellar populations. If encrypted signals correspond to artifacts induced by interaction with classified assets, protocols governing orbital object disclosure may require revision. If perihelion triggers acceleration or deviation from expected trajectory, the planetary defense community must reassess its risk parameters for future interstellar encounters. Every what if branches to further uncertainty. What if outgassing at perihelion is observable in the infrared but not the visible? What if the coma grows but dust production remains low? What if secondary fragments carry a signature of noble gases or release polycyclic aromatic hydrocarbons in unprecedented quantity? What if spectral analysis at high resolution yields lines corresponding to materials known only from laboratory synthesis? What if data is acquired by classified telescopes in orbital position, but findings are not returned until weeks after event threshold passes? The infrastructure is comprehensive, but analysis is limited by human attention, institutional caution, pipeline configuration, and serendipity. Sensor arrays are finite, priorities can be shifted if new anomalies appear, but bureaucratic inertia does not always yield to urgency. If observation teams strategically prioritize certain scenarios over others, blind spots emerge, areas of the datasphere left unexamined, conclusions deferred. Peer review, publication, proprietary periods. They are meant to ensure rigor, not secrecy, but as token after token of institutional caution accumulates, the system drifts from real-time investigation to retrospective reconstruction. October 29th will reveal more than spectral ratios or dust curves. It will answer, directly or by omission, the degree to which science is prepared for the anomalous, the unprecedented, the event that forces revision of theory, protocol, and practice in ways not easily undone. Yet as you watch the silences accumulate, you understand synthesis is slow, answers are deferred, explanations are always contingent, the signal is real, the patterns are discernible. The investigation continues, even as the object moves further from certainty, further into the reconstructed realm of memory, archival data, and collective anticipation. Every detail, every uncertainty compounds. The size of 3I Atlas alone is a provocation. 33 billion tons, as inferred from the infrared thermal curve, is an outlier among interstellar intruders of record, its scale not explainable as a mere statistical tale of ejection energies. Statistical arguments falter. To account for an object of this mass implies a source region of entirely different population or an ejection mechanism we do not catalogue in planetary system formation. You work through ejection models, giant planet scattering, tidal stripping, binary star disruptions, yet the numbers do not fit unless you assume something non-random, a cluster ejection, a destabilized circumbinary, or something artificially timed. Each scenario carries its own impossibilities, its own signature of an event not yet captured by the theory. What if the nucleus is stratified? layered from episodic thermal events, accretion surges, interruptions of galactic journey by supernova shockwaves. Sublimation curves projected for single-component ices do not predict this outgassing profile. No single set of volatiles explains carbon dioxide dominance so extreme and early, nor the sudden onset of cyanide and absence of formaldehyde. You imagine a composite structure, an inner core unaltered since birth, capped by tens of meters of radiation, processed resin, maybe regions of clathrate hydrates trapping noble gases at abnormal proportions. What if perihelion cracks the outer shell, and a new, more volatile, rich chemistry erupts, one that has not even been documented in the preliminary spectra? Such an event would generate not just jets but true localized explosions, sending dust sheets or even fragments onto diverging hyperbolic orbits. Secondary nuclei, brief new comets birthed in the glare, each carrying subchemistries and timelines of condensation, instantaneous formation of a genetic family in real time. You consider the anti-tail again, its persistence, its slow evolution, the fact that large grains remain sunward longer than solar wind models predict. Cohesion mechanisms, electrostatic, organic binders, ferromagnetic domains, each have implications for formation. If it is organic cohesion, are we seeing a comet rich in prebiotic chemistry, the kind that seeding models invoke for the early Earth? Or is the anti-tail a product of rotational dynamics so unusual, a stable orthogonal spin axis preserving grains in a preferential plane, that it points toward a history of tidal sculpting or ancient collision? If precession or slow modulation appears after perihelion, it could be a sign of internal redistribution or transient loss of mass, even a precursor to total disruption. Nickel emission without iron deeper analysis reveals that the thermal environments required for nickel-carbonyl formation are rare outside the laboratory. The volatility, the chemical instability require precise cold trapping conditions. Laboratory analogues have only simulated such environments in molecular beams and cryogenic traps. If detected in an interstellar object, it implies the presence of gas phase chemistry not yet incorporated into Comet models, reactions that occur far out, not upon sunward passage, but during migration through molecular clouds, or even during hypervelocity passage through the heliopause. The failure to detect iron pentacarbonyl is more than a gap, it is a direct challenge to cosmic condensation sequences assumed to be universal. The early water outgassing, beginning a full astronomical unit beyond standard comet activation thresholds for water ice, suggests localized energy sources, radioactive decay of short-lived isotopes, unlikely, but not impossible for fragments of planetary crust, tidal friction from ancient close approaches, or catalysis within clathrate matrices prompted by cosmic ray impact. If a period of late, rapid brightening follows perihelion, it may indicate that internal energy release is staggered, venting through transformed conduits only after the insulating mantle cracks fully under solar stress. If, instead of outburst, the outgassing dwindles, the coma-quenching scenario emerges, pointing to a composition of metastable polymorphs or to a heat-triggered endothermic reaction layer pooling solar energy before locking it in latent transitions. Such material science is only beginning to be modeled, and only in terrestrial cryogenics. Trajectory calculations, although robust, rely on thousands of precise astrometric measurements. If, post-perihelion, even a small non-gravitational force appears, a decimeter per second squared deviation consistent across observational stations, models of outgassing recoil must be revised, and the possibility of internal venting unevenly distributed or even mechanical action cannot be wholly ruled out. What if, undetected, a burst of activity at conjunction, unobserved behind the Sun, shifted the object by a measurable but unexplained margin? The error would propagate, leaving predictions subtly wrong, findings ambiguous, explanations scrambling to catch up. Instrument failure, cross-calibration errors, unsynchronized pipelines, each become indistinguishable from genuine anomalies if not meticulously recorded and openly discussed. The multiplicity of observational assets promises redundancy, but only if comparison is timely, if schedules overlap, if data is released. Otherwise, the same event is explained 4 different ways in 4 different epochs, each account segregated behind policy walls. ExoMars and Mars Express, both reporting inconclusive results, spectra acquired, signals in possession, data not released. You note how inconclusive becomes a shield for the complicated, the insufficient, or the inconvenient. It becomes especially protective when combined with long proprietary periods and press statements that highlight technical achievement rather than scientific result. The intercepted transmission, 40 seconds of modulated signal encoded in patterns consistent with known telemetry, originated from the region where 3I Atlas transited during solar conjunction. It lingers in public forums as a Rorschach test for speculation. Is it an artifact of a solar event? Is it a byproduct of interaction between cometary plasma and a high-gain antenna? Is it intentional, embedded, deliberate? In the context of concurrent rumors, event threshold alpha referenced, it becomes a Rosetta Stone only if more signals appear, only if the pattern is repeated and the content, eventually, is rendered intelligible. Spacecraft coincidentally positioned, Europa Clipper, Hera, Parker Solar Probe, all intersecting the predicted ion tail in the days bracketing perihelion. The public narrative is routine, flight plans unchanged, data collection scheduled as opportunity allows. Yet both missions' sensor suites dwarf the capabilities of any probe ever passed close to interstellar material. The probability of concurrent traversals strains not just credulity, but forecasting of what is routine. What if these fly-throughs yield not just enhanced plasma readings, but molecular ions incompatible with solar system chemistry? What if an energetic particle spike is observed, brief, unrepeatable, at the predicted crossing? What if anomalous magnetic data, conflicting with Parker's long-term field model, emerges precisely where simulation predicted interaction with a comet tail thicker or differently composed than theory permits? And what if all this is witnessed, catalogued, yet embargoed under non-public review? What if proprietary science becomes a holding pattern not just for professional reward, but for deliberated narrative? If institutional response is not merely careful but convergent, aligning so precisely with extraordinary events that the meaning of care slips from prudence to reticence, from protection to control? Peer review. Normally a guardrail, here becomes a dam, to be lifted or maintained as gatekeepers decide that uncertainty or certainty is mature, that the story can be told. But the object will have moved on. The afterimage in the archives will remain to be re-examined, rescored, its lessons always a few months behind its light. You track researchers' tone in public statements. When even the cautious couch hypothesis as preliminary, when calls for more data, grow more urgent as public intervals lengthen, it becomes hard not to sense the pressure, the awareness of a window closing. The more exceptional the data, the slower the process becomes, public transparency narrowing in direct proportion to the anomaly's challenge. This is the paradox. Theory demands revision, but protocol delays the moment when anomaly becomes revelation. The event horizon is October 29th. Afterward, what was hidden physically in solar glare, institutionally behind embargo, will either present interlocking conclusions or deepen mystery. Perihelion marks not just a crossing, but a release, not an ending. A beginning for the next layer of analysis, the next recalibration of theory, the next cycle of anticipation, skepticism and transformation, as the system strains to catch up with a reality delivered at velocities and depths no model dared to expect. The deep ice layers, untouched for epochs, could be a record of nucleation events stretching back to molecular cloudbirth. Each micron a localized portrait of galactic chemistry, frieze fractured by passage through spiral arms, shock fronts, or even supernova debris. Laboratory analogues simulate only a handful of cycles. Here, millions may be inscribed in atomic strata, a palimpsest carrying unknown volatiles, isotope ratios, and the imprints of radiolytic restructuring. If heating at perihelion triggers stratified outgassing, the data will reveal snapshots of past eras, different volatile bands activating sequentially, mapping chronology into the expanding coma. Secondary object formation is a plausible outcome if the nucleus disrupts. If stress exceeds cohesion, if vent outbursts puncture weak zones, the progenitor could produce satellites, each tracing a faint echo in the dust, forming a transient family before dispersing along diverging hyperbolas. Observational precedence exists for such fragmentation. Shoemaker, Levy 9, 33-2p, IKEA, Murakami, but never for an interstellar visitor. The consequence, new objects would recalibrate tail morphology, increase dust density, introduce chaotic variables to trajectory predictions, and set new constraints on formation models. The dust composition remains a cipher. Particle size dominates at the millimeter scale, yet spectral slope analysis suggests complex surface chemistry. Red coloration, visible slope near 20% per thousand angstroms, recalls tholins and refractory organics accrued over cosmic timescales. Magnetohydrodynamic anomalies may arise if charged particles or fractal dust aggregates interact with solar wind, generating micro-instabilities, modulating field line orientation, producing flickering signature in the plasma tail. If Parker Solar Probe's magnetometer catches such fluctuations, magnetospheric models may need revision for the behavior of non-solar magnetic seeds. Before perihelion, mapping plasma tail geometry is straightforward: ion flow, solar wind density, predicted interaction angles. After perihelion, tail restructuring lags behind the changing energy input, a time-dependent knot of plasma, dust, and energetic particle injection. Galactic trajectory calculations complicate interpretation. Each minor deviation, each unexpected boost in velocity, each unmodeled trajectory twist reopens analysis of galactic tide effects, interaction with massive compact objects or non-baryonic mass concentrations that might have influenced entry direction. No historic analog fits, Oumuamua, Borisov. Each told us something of interstellar chemistry, but neither carried the mass, anomalous composition, or multi-layered silences documented here. Speculation about formation veers into zones of uncertainty: binary star ejection, disk instability, supernova shock imprinted protoplanetary structure. Rotation period stability, lack of precession or nutation, hints at a coherent interior structural regularity that, against expectation, survived cosmic ray bombardment and gravitational encounters. If rapid orbital adjustment occurs at perihelion, the implication is forceful and immediate. Outgassing vectors reshape trajectory, or something more complex, a non-gravitational impulse, perhaps mechanical action, perhaps another physical process. Shape irregularities, mapped in photometric light curves, may evolve. Surface vents could collapse, spin axis tilt, or modulate, revealing the consequences of internal structural realignment or the impact of previously hidden reservoirs activating. Observational delays, gaps in data synthesis, and incomplete records become consequential in this context. Swift, Hubble, Webb, Keck, they form a woven net, but any failure, any missed integration, any fragment of the record lost to timing or proprietary protocol leaves knowledge gaps that may never close. Cosmic ray impact modeling, high-energy transient detection, calibration of thermal emission, all form layers of data whose integrity depends on the system working perfectly. In reality, systems break, data may be lost, miscalibrated, contested, or embargoed. If the nucleus disintegrates, unmeasured fragments may remain, stray debris caught in the glare, potentially undetectable until analysis lags catch up. Loss of contact with secondary bodies would create new observational imperatives, but might also expose sensor limitations, instrument range, and pipeline speed. The possibility of symmetrical outgassing, layering of isotopic ratios, or emergence of noble gas bands creates a landscape where each new variable feeds retroactive modeling, science chasing the tail of an event already evolving beyond the reach of prediction. The aftermath is analysis. Months, years, perhaps decades of post-event data, calibrated against only partial records, constrained by what this brief proximity to the Sun has revealed. Knowledge gaps may persist, biasing future models or, if integrated well, rewriting our understanding of protoplanetary disk diversity, chemical evolution, and galactic object migration. This is the consequence of complexity meeting uncertainty, a slow untangling, a recursive investigation, always shaped by the timing of what was seen, when it was seen, and who was able to look. Every aspect of the dust-tail morphology resists simple explanation: large grain dominance, weak small particle population, and the anti-tail's improbable persistence sketch a tableau of evolved cohesion mechanisms. Electrostatic binding, organic cements, or even unknown refractory processes may be at work. Tholins. Long-chain hydrocarbons constructed by cosmic rays in deep-time stratigraphy coat millimeter grains, generating resilience against solar radiation, red slope in spectra, and perhaps anchoring larger aggregate stability. If post-perihelion microfragmentation occurs and the tail erupts into symmetrical partial arcs or late-blooming dust storms, the system will model those, yet explanations may always lag behind the observations, each flaring episode an afterimage of a process too rapid for theory to preempt. Noble gas banding, if it emerges in the spectra, would be revolutionary. Argon, neon, or xenon trapped in deep ice indicates either formation in ultra-cold regions or subsequent galactic passage through environments of high inertial enrichment. Unlike carbon dioxide or water signatures, noble gases do not easily fractionate. If they outgas in stepwise bands, the event would flag deep repository venting, a sudden conduit traced to ancient pockets, now opened by perihelion flare or internal fracture. Such outbursts could trigger fragmentation not through normal pressure buildup, but by structural fatigue, fissures opening, chunks shearing free, launching into high-velocity ejection along the sunward vector. High-velocity dust, laced with abnormal chemistry, becomes the tracer for system-shocking events. If anti-tail persistence survives weeks past perihelion, grain cohesion must be modeled as a multi-regime system. Theorists would investigate the possibility of cometary family formation, daughter bodies evolving in situ, carving new orbital footprints, each a residual memory in both the archival record and the solar system's evolving population statistics. Dust composition in this case would seed hypotheses for outliers in both isotopic ratios and particle architecture, documenting in one apparition what has only been suspected from more distant analogues. Sensor glitches, loss of signal with secondary nuclei or fleeting features become systemic variables, propagating error, reframing analysis, always threatening to metamorphose oversight into theory bias. Later, as archival synthesis advances, the record's gaps shape the knowledge legacy. Whether recalibration catches anomalies or ingrains them as artifact, interpretation may drift, echo observations stitched into event narratives whose boundaries are always negotiable. Magnetohydrodynamics, field lines warping, plasma density mapping surging in cometary storms, these become the heartbeat of interaction with the solar wind. If the field spikes registers an anomaly as tail particles punch through typical density boundaries, the theoretical consequences will ripple. Is it the signature of new science? An unmodeled energetic phenomenon, or the final debut of a process occurring in the heliosphere since before solar system formation but never before caught in the act? Outburst triggers might point to internal pressure regimes unknown in traditional cometary physics. Perhaps zones of volatile-laden matrix, layered over eons, undergo a sudden systemic nucleation. Latent energy releases instantly, not as a gradual evaporation but as a cascading transformation, transmuting a cold monolith into a cloud of fragments, each a petri dish of interstellar history. Such a phase change, if captured, would upend models of protoplanetary disk evolution, feeding into entirely new frameworks for understanding how objects cross gulfs of time and distance resilient enough to teach us about distant systems. Each detail captured now, each feature explained or left ambiguous, will become a reference in future catalogues. Theory will evolve to mirror not only what was observed, but what was missed, what was doubted, what was enshrined in silence when observation and institutional rhythm fell out of phase. What remains is the expectation, persistent as dust, that the next anomaly, should it arrive, will find us either better prepared or looking again, asking what we failed to see or failed to imagine when first given the chance. Volatile outbursts punctuate the narrative, unexpected, sometimes explosive releases of gas that defy standard thermal modeling. When the coma collapses or shifts, whole regimes of dust-grain charge and particle polarization become measurable by high-cadence photometry and spectropolarimetry. Dust grains, especially in a chemically anomalous coma, may acquire non-standard surface charges, interact with solar wind more dramatically, or even self-organize into refractory debris sheets that echo long after primary outgassing events end. If episodic venting drives secondary tailbirth, observational cadence and instrument wavelength coverage will decide how much of the layered structure is recognized in time, how much remains hidden behind sensor latency or thermal noise. Rotational evolution provides another axis of ambiguity. The 16-hour rotation period, stable yet exposed to energy gradients and impact signatures from venting, may shift subtly, revealing internal pressure regime changes or analytic errors. If the rotation period abruptly changes, models must explain mass redistribution, internal gas phase transitions, or perhaps the mechanical impact of debris loss or fragmentation. Light curves may show anomalous dips, non-thermal emissions indicating magnetic spikes or undermeasured fragments, each detail a possible index of forces moving below the surface. Solar wind deflection and plasma tail modeling confront the multiplicity of observational delays and tracking failures. If instruments miss critical transitions, recursive observation protocols may pick up echoes. Late phase mapping, fragments lost then recovered, or serendipitous coincident data as spacecraft pass through the evolving zone. Particle flow reversals, changes in ion charge balance, and asymmetrical magnetospheric readings trace influences both intrinsic and environmental. A comet's atmospheric evolution mirroring its external dynamic interactions. Each new measurement, each anomaly, feeds incremental synthesis, ratchets up knowledge divergence. Time-locked data releases, review embargoes, chemical outlier reporting, these build into systemic oversight, where hypothesis drift becomes inevitable, archival errors propagate, and what is public knowledge diverges from what is internally known. Observational serendipity, the chance capturing of a dust streamer or late fragment, becomes a ragged lifeline for those recalibrating models, for those reconstructing the event in hindsight. Institutional protocol enforces silence, slows theory's pace. When a sensor artifact is recognized only after data release, whole sequences of analysis may be rendered provisional, feeding into quieter speculation and retroactive modeling. Fragment loss, secondary nuclei, or shifting debris fields may never fully reappear in the record, their place uncertain in the timeline, their contribution to the broader narrative an echo against the silence left in their wake. The knowledge legacy, therefore, is layered. It is never simply what was observed. It is the living record of error, serendipity, protocol, synthesis, and the ever-present reminder that each event will be interpreted anew as both immediate revelation and long-term question by those standing at the boundary of what is known and what remains resolutely unspoken. Cross-institutional analysis, when possible, forms the backbone of theoretical recalibration. Infrared anomalies collated against dust density evolution, plasma tail bifurcation mapped beside solar field interaction, time-lagged peer review layering, consequence mapping upon archival ambiguity. Every opportune observation, each spectral transition, feeds directly into the case study synthesis that charts not only outgassing frequency or tail geometry, but the signature of non-random events. Cosmic ray spikes, magnetosphere discontinuities, mass loss tracking, all resonating in the corridors of inter-observatory contention. Late data acquisition often means knowledge must be reconstructed from echo, not substance. Outlier reports, theoretical hypotheses, and observational oversights accumulate in the knowledge base, yet diverge the moment institutional protocol and notification lag stifle rapid hypothesis formation. When unresolved data epochs stretch between release schedules and embargo policy, adaptive modeling becomes a necessity. The system bends. Archival uncertainties become both the context and the constraint on what new science can recognize, the lesson history teaches every time an object leaves the window of active inquiry. Comet tail geometry, bifurcation into distinct current-driven plasma channels, may not match ordinary solar interaction models. A tail splitting, driven by layered signatures or episodic outgassing, hints at deep composition changes or latent reservoir activation. If spectral transitions register abrupt change, if light curves show non-thermal emissions uncorrelated with solar phase, theory must adapt, must account for transition timescales, must interpret not only data but its absence, not only noise but the structured silences in the record. Rapid hypothesis formation, always at risk of theory lag from time-locked data, competes with incremental synthesis for priority. Each institution's cadence determines when contention arises, when consensus coalesces, or when archival errors propagate unchecked into next event anticipation, shaping what is learned from what was lost, framing every question about future object encounters in language shaped by the incomplete patterns of the present. Inter-observatory contention is not dysfunction, but the natural pulse of science at the edge of knowledge. Researchers, constrained by institutional silence, pass fragments, search for consensus, and, when forced by timing and consequence, push for cross-release and comparison even while theory drifts in uncertainty. Late-phase mapping, tailored to maximize utility in the narrowing window of comet proximity, must reckon with observational oversights, data pipeline interruptions, and the shifting architectures of access. Loss and recovery mean more than physical fragments. They are states of knowledge, gains revoked and then reinstated as synthesis proceeds. Each time knowledge diverges, every time theory drift prompts recalibration, the legacy of the observation, its failures, successes, blind spots echoes forward, setting the terms for how the next anomaly, the next perihelion, the next enigmatic signal will be assimilated, challenged, or preserved against the background of a world still learning how to ask the right questions at the right time to the right entities from the right vantage. The anticipation persists. The narrative is unfinished. The story, as always, is not in concluding, but in what remains to be seen. Systemic knowledge fragmentation is not just a matter of policy, but a lived reality, a consequence of data embargo, publication bottleneck, and the innate inertia of institutional caution. Real-time synthesis, when it occurs, is the product of intercalated reporting and serendipity moments when adaptive review or anomaly triage are prioritized over cadence, when theoretical flexibility outpaces procedural constraint, and when the event chain of interpretive risk is briefly open. Memory-based reconstruction becomes standard. As each non-linear timeline of release and embargo layers, sequential uncertainty accumulates. Cross-mission contingency, whether forged by convenience or strategic calculation, is the quiet thread that can pull knowledge out of silos. If calibration protocols and data redundancy are robust, if transient detection is correctly aligned. Feature decay, outlier trajectories, and residual signals may persist in the record long after the main event. Tracing those signals, mapping collaboration thresholds, becomes the task of legacy analysis. Institutional inertia, even when justified, leaves knowledge inheritance maladaptive. Observer bias is endemic, response strategies shaped by disaster readiness, but rarely by maximal openness. Post hoc modeling, the statistical stitching together of after-the-fact data, authority and ambiguity, is often the only recourse. Lessons retained, drift, cadence adapts, but technological frontiers remain constrained by publication bottleneck and the friction of strategic caution. Future event preparation is changed by each lesson, each interpretive lag, each recalibration of protocol, as contingency planning becomes less about the technical and more about the communicative and strategic. When data is fragmented, when reports are embargoed, the gap between what is known and what is possible yaws wide, challenging researchers to operate at the interface of theory, memory, and live uncertainty. What persists is not simply the object or its passage, but the cumulative effect of how data was moved, how serendipity was or was not leveraged, how systematic analysis was performed or deferred, how interpretation was shaped by thresholds that obeyed not just epistemological caution, but the incentives of the system. In that landscape, the real chain of consequence is less the object's chemical anomaly or perihelion event than the process of observing, interpreting, explaining, and, ultimately, remembering. The lesson is perpetual. Every event, every anomaly, every silence feeds into an evolving capacity for recognition and response, its traces carried forward not only in the facts left behind, but the architecture of knowledge built, deliberately or by necessity, to accommodate futures we cannot yet foresee. You have been following the story. The official version is public, but the undercurrents, technical, procedural, and scientific, run far deeper. Atlas survey sites log observations, their automated routines detecting movement and light, but from the beginning, Third-Eye Atlas has not conformed to expectations. The preliminary datasets, hyperbolic trajectory, eccentricity of 6.2 persistent deviations from all solar system models were logged, delayed in processing, reviewed before wider flagging. 12 hours may be within parameter, but it denotes a bureaucracy tuned to caution in the presence of anomaly. The mass is staggering, 512 kilometers across, up to 33 billion tons. This scale for an interstellar object is statistically unjustifiable by random ejection, and every piece of orbital analysis strains the limits of what existing ejection models predict. 58 kilometers per second. Such a velocity is the mark of deep cosmic history, an origin story that recalibrates the limits for what planetary systems can lose and the galaxy can accept. The trajectory is ecliptic, aligned, a probability anomaly too coherent for statistical comfort. In the language of planetary architecture, it means either coincidence or agency, an alignment not random, a path that threads through orbital highways as if sequenced. Passing Mars at exactly the window when the ExoMars Trace gas orbiter could observe, producing images marked by diffuse glow and uncalibrated brightness flicker. Spectral results pending, a phrase that suspends direct knowledge under the guise of ongoing calibration. When the object entered solar conjunction, a blackout descended. Any ground-based telescope lost the object, with all public observations silenced precisely before peak perihelion interaction. The infrastructure is robust, pipelines and proprietary periods enforced, the process designed so data enters the slow current of exclusive access. Hubble, Webb, VLT, Keck. Each observing, each dataset governed by embargo, each finding subdivided into controlled purviews for months, sometimes years. Only fragments escape, in press releases, conference abstracts, and the strategically delayed preprints. None to be considered verified until the full chain proposal, execution, calibration, peer review is complete. The chemical signatures are unambiguous in their ambiguity. Webb sees a coma of overwhelming carbon dioxide, 6:1 over water vapor, an unchartable deviation from any solar or interstellar precedent, ratios extreme enough to force theorists into deep time and exotic disk formation scenarios. Meanwhile, the object's surface, electronically red and spectrally steep, is marked by tholins and refractory organics unlikely from brief galactic exposure alone. This is a surface built through eons, polymorphic, altered by cosmic rays to a depth unmeasurable except by the progress of sublimation itself. Atomic nickel, strong and persistent in the VLT data, unaccompanied by iron, a puzzle that suggests rare gas phase compounds, peculiar molecular carriers, or processing conditions entirely absent in the known astrophysical playbook. No methane, no ammonia, no acetylene, no ethane, no formaldehyde. A chemical sparseness that is either the signature of harsh cosmic processing or a clue to genesis in an environment whose parameters are only now being theorized. Every competing explanation formation at the Kui ice line, deep radiation processing, peculiar disk environment demands data still sequestered by embargo and delay. Dust morphology repeats the cycle. Large grains persist, small grains absent, the anti-tail sunward and remarkably durable, the distribution more consistent with electrostatic or polymeric cohesion than with solar system dust mechanics. The coma, initially compact, is asymmetric, resisting the simple impulse of solar wind modeling. Each new observation, whether high cadence or one-off, suggests instability or perhaps orchestrated emission, particle streams forming and dissolving as if the nucleus itself responds to deep, periodic stress. Throughout, coordination is both real and a source of further ambiguity. International Asteroid Warning Network, NASA's PDCO, coordinated exercises, the timings coincidental but uncannily efficient, every critical campaign begins or ends just outside the window, most likely to contain unambiguous evidence of anomaly. Spacecraft in transit. Europa Clipper, Hera, pass through impact zones mapped months in advance, scheduling flexibility under nominal status, yet unannounced adjustments and in-situ measurement opportunities multiplied by alignment, probability too tight for pure chance. Simultaneous, encrypted transmissions, technically plausible as noise, yet arriving during the conjunction blackout, are logged but left unexplained. Rumors proliferate, structured in the absence of official release. Section 7 protocols, black budget asset targeting, event threshold alpha. These pass through digital networks, flash through social corners, drawing inference from patterns in what is omitted as much as in what is said. Official statements emphasize transparency for the first time. Never before a focus with Oumuamua or Borisov, framing abnormal caution as evolutionary adaptation in planetary defense, yet always deferring judgment until data is processed, reviewed, verified. Peer review, once a mechanism for the healthy pacing of fact, is now a filter through which every ambiguity is washed and deferred. Preprints proliferate, each paper declared unfit for citation, questions and answers alike embargoed beneath draft watermarks and disclaimers. Proprietary periods run their clock, and only the authority of those holding exclusive access bridges the gap between private knowledge and public speculation. Public statements, when they arrive, are studiously non-committal. Rare is the researcher who strays from model language, and rarer still the admission, except at the edge, that a chemical, trajectory, or electromagnetic feature is inconsistent with standard models. The call for more data becomes a mantra, repeated endlessly, replacing conclusion with process, verdict with patience. And still, every physical parameter points beyond precedent. The object is large, fast, chemically extreme, visually dynamic, acoustically and spectroscopically enigmatic. Every explanation, natural or otherwise, demands new models, new coordination, new transparency, a new agility of inference. Dynamics of outgassing, plasma tail bifurcation, magnetic discontinuity. Each detail is logged, embargoed, queued, a signature waiting for the cosmology of the future. October 29 approaches. Perihelion is a crucible, a boundary condition not just for the object, but for the system of knowing itself. If 3I Atlas is a comet, then our catalogue expands, the system adapts, and uncertainty narrows. But if the patterns, the persistent anomaly, the silence, the unmodelled events, the rigorous fragmentation of knowledge by schedule and bureaucracy, persist, then the event's true outcome is not measured just in data points, but in the recalibration of every threshold of plausibility, every assumption about what can enter, transit, and leave our system, and every idea we hold about what information is observable, sciable, and ultimately shareable. Somewhere beyond the last calibrated image, the object keeps moving, trajectory uncoiling through space, unchanged by observation, undisturbed by theories left unfinished. The data will linger, and the silence with it. For a moment, everything holds its place, the record, the absence, the unanswered question balanced just out of reach, waiting for what comes next.